All right, so yeah, I hope you guys are doing okay with understanding the material that we talk about. So welcome to session 3 of the Fundamental Statistical Tools workshop. We'll definitely go again through some of the stuff we already talked about. We'll practice some of the coding again. And today, okay, you will see there is quite a lot to go through. So hopefully your heads don't explode by the end of this session. If we don't have time to cover some of the materials we wanted to cover, we will simply, transfer it to the last session next week. Okay, let's just dive right in. Okay, so if you remember last time, we did a t-test because we were interested in knowing if we had a difference in means between two groups. So we have this data set that we've been using with leopards. So yeah, a fake data set with fake leopards, but still data nonetheless. And two locations. And we were simply wondering, okay, we can, is the body condition, which is one of the variables that we had for that data set, is the body condition on average different from one location to the other? And the t-test was suitable for this, but we'll actually explore in more details why it was suitable. And we found a significant difference. And we'll also go through this again a little bit, because last time we didn't have much time to expand on what this all means. But the point being is that, yeah, we looked at the means, and the question was that, okay, the means are different, of course, like it would be very unlikely that they are exactly the same. But is that statistically significant or not? Do we decide to conclude that this is that they are actually different or that they are the same? Okay, so first off, with most tests and with most modeling or statistical approach, there's going to be assumptions associated with your methods. So especially parametric tests have usually a few assumptions. We mentioned non-parametric tests last time, just to say when you violate some of these assumptions that parametric tests require, you usually there's usually a non-parametric version of that test that you can use instead because you are violating these assumptions. But we'll stick to parametric tests. So let's look at what these assumptions are. And to take as an example, the student's t-test assumptions, which is the test we've been using. The first one is that the data should be continuous. So t-test should not be used for other kinds of data. So that's fine. We know we have continuous data. The BCI was the body condition index that we use to compare the means in the t-test was continuous. So no problem. The second one here on this list is that the data should be approximately normally distributed. And we decided that it was, but that's what we're going to look into a bit more details right now. The third assumption is that the data points should be independent. So that's to say, during your sampling, you should not, for example, sample the same leopards twice, but others only once. And if you simply run a t-test, then, well, the test doesn't know that you sampled some leopards several times and others not. So some data points are not independent of each other because they come from the same animal. That's what this means. We know from this data set, I'm the one who made that data set, so I can tell you that these data points are independent, so no problem. Yeah, so this, for example, and these assumptions are really for the two sample t-tests. Because if you remember from last time, there is another version of the t-test which can compare the same leopards if there's like a different treatment, which is a paired t-test, right? So in this case, okay, you have a set of leopards, you put them through a treatment, maybe you move them to a different location, and then you measure them again. The way you calculate this t statistic is a bit different, but it's still a t-test, just a different kind of t-test. we used a 2-sample t-test. We're comparing 2 samples and we're assuming everything is independent. We're not sampling the same individuals twice. And another assumption is that the sample should have a similar amount of variance. So remember, a variance is a measure of spread of the data. Like, how much do the data really differ around the mean? And we looked at, I think, at some box plots, and we decided to say that yes, the variance seem relatively similar. One thing to keep in mind is that the t-test assumptions is not, how do you say, they're not always very strict, in the sense that the test itself is quite robust to violating slightly some of these assumptions. For example, normality, even if your data is not completely normal, if maybe close to it, but you could say maybe not really, it will still be quite robust to that, for example. Okay, so when we looked at, so we performed that t-test, we thought, okay, all the assumptions have been met, but okay, how do we test for these assumptions? The first method, and that's the one we used last week, was a kind of graphical inspection. We just look at some graphs and decide to say, okay, the assumptions are met. So that's the first method. You can use a histogram to check normality. So if the data is normal, you should see a lot of values around the mean, and then the further away you walk from the mean, the less likely it is you find individuals within that range. So it should look a little bit like the histogram. Well, I'll just show you the histogram. So for each location, looks like this. And we do have a lot more leopards that have a BCI that is close to the mean, especially for WCAN. The WCAN, sorry, the N was cut off on the label. So that's, yeah, the WCAN location is very normally distributed, it seems. Altai, okay, it still seems reasonable, but there's a bit more spread, it seems, at least. Like there's a bit more values that are further away from the mean. But upon expansion of these histograms, we can say, okay, it seems like they are relatively, within each group, there's relatively normality here. Also, keep in mind that we don't have that many samples. We don't have, in each group, it's about 50 leopards each. So of course, you won't have like a perfect bell-shaped curve that you would expect from this normal distribution. Just to remind you, this is the code to get these histograms. So we created one object, which is simply the vector of numbers for the BCI at WCAN, another vector, another object called BCI Altai. So if you just input this into the histogram function, which is just hist, then this is what R will return. You can try it on your console. Okay, now for homogeneity of variance, similarly, you can look at box plots, because box plots do tell you about the spread of the data. It doesn't look at the variance though, so be careful in your interpretation. This is the code. So the function is called boxplot. This is a formula notation. Anything on the left, well, the factor that is going to be left of the tilde is going to be your y variable. So this is going to be your y-axis. Location for a boxplot, at least, it should be a grouping variable. So if you put a continuous variable here, I think you'll get an error. You need to specify the data you're using. So if you're using columns in a data set, R needs to know what data set it comes from, because otherwise it will look for an object called location and another object called BCI2, which don't exist because these are simply the columns of that data set, which is why we need both the formula, but also the data these variables come from. So now if we look at the box plots, the first thing we can see actually is that the median, which is the dark line here, we can see that the median is slightly higher at WCAN, which can tell us a little bit already about what the t-test result might be, is that we might find a significant difference, maybe with WCAN having a slightly higher BCI than Altai. So that's what the test will be for. We'll be testing that. And we can see that the size of the boxes is not dramatically different. Again, this does not tell you, this is not the variance or the standard deviation. These are the quantiles. So the first and third quantile, I think, yeah. But yeah, just to say, okay, there seems to be a bit less variance in Wacom. The variance seems to be slightly smaller, plus a couple of outliers. Let's see. So if we check this graphically, usually it's fine. Some people will do it that way. Some people would prefer to use an actual statistical test to test these assumptions. So this is the second method you can do. To check normality, so there's not just these tests that I'm going to mention. There are other tests you can use. These are not the only ones. But the most common one to use to test normality is the Shapiro-Wilk test. This is how you can invoke the code. This is what you can write in your console in R to perform that test. So it's simply Shapiro.test, that's the function, and in between, again, we're going to test normality for each of these groups. And we already have that object called bci.vacan and bci.altai, so we'll do it for both. And these are the two summaries that we get for that test. The statistic here is W, so this is the value of the statistic. And you have a p-value associated with it, but we'll talk about p-values a bit more. If your significance level is 0.05, like people usually use, here we can say that the p-value for both groups actually is way above 0.05. It's at 0.7 for this. If it was less than 0.05, we could conclude that at the 95% significance level, we could say that the data is non-normally distributed. If it's more than 0.05, which is the case here for both groups, then we can say with confidence that these data sets are normally distributed. Okay, so that reinforces what we concluded from the histograms. And secondly, to check homogeneity of variance, there's also a test you can do. Again, not the only one. The one I'm showing here is called the Bartlett's test, which actually assumes that the data is normally distributed. That's one of the assumptions of that test, but we just checked that, so I think we're good. And this is how you call it. It's that line, that's the function. This is also, these functions are also embedded in R, so you don't need to load any extra packages to run them. And you'll notice this is the same notation as the box plot. We use a formula. So the y-axis is the BCI, and we're going to look at by location. And this is going to test, okay, is the variance similar for both of these in both locations? Again, we specify that the data is UNCIA, that our data set. And this is the summary. We have a k-squared this time, that's the value of the statistic, and the corresponding p-value is 0.1, which is more than our significance level of 0.05. So again, we can conclude that the data is reasonably homogeneous in their variance. Okay, so now, okay, we've mentioned p-values a few times. I'm sure a lot of you will have heard about the p-value before, but let's just explain a bit more what the p-value is. So remember, when we do a two-sample t-test, this is the formula. This is how we calculate the t-statistic. So if you have the summary, so just to remind you how to run this code, we created that object by subsetting UNCIA BCI2. So we want BCI2 to be the vector of numbers from there, but we only want when UNCIA location is Wakan. So with that function subset, if you remember how to use it, this will give you a vector of numbers, which will be the BCI values, well, specifically BCI2, which was the second method we used last time, for that location, for that Wakan location. And we call this object BCI Wakan, because now we know exactly what this object is. We do the same for BCI Altai. And we perform the t-test. So the t-test will be, okay, the first group will be BCI Wakan, and the second sample will be BCI Altai. These are default, actually. The alternative argument here is a default, so I don't actually have to write it in there, because R will actually have this by default. I just put it there so we are very explicit about what we're doing. Two-sided means that we don't expect one sample to be bigger than the other or smaller than the other. we don't know in which direction it will go, which is why we want to do a two-sided test, two-tailed test it's called. If we thought VACAN was going to be bigger and we want to test specifically that question, is VACAN has higher BCI on average than ALTI, then we could put one-sided. We put var equals true. That says that we are assuming that the variance is homogeneous. We even tested for it, so it's fair to put this argument. Although by default, R will use a different version of the t-test. So assuming that that is going to be robust to violating that assumption. Here we want to perform the t-test, so that's why we put var equal true. So that's another argument of the function. If you want to remind yourself again of what the function does, the t-test, you can always remember put question mark t-test, and then in RStudio you'll have the documentation for that function. All right, so these are the results that we got from the two-sample t. So R reminds you what you did. You did a two-sample t-test. This is the data you used. The t-value is 4.7. Degrees of freedom are 101 because it's going to be the size of the first group -1 plus the size of the second group -1. So essentially the number of cases -2, which in our case was 103 peppers -2 because two groups. And the p-value associated with that t statistic is very small, as you can see. It's 8.1, 10 to the power of -6. So we have 6 decimal places. It's way below 0. The alternative hypothesis, which is what we would use if the p-value is below our threshold, is to conclude that there is a true difference in the means, and so they're not equal to 0. So the true difference is not equal to 0, meaning there is a significant difference between the two means, between these two samples. It also gives you the sample estimates, so the mean of X and the mean of Y. So the mean for VACAN is 0.73 and the mean for ALTI is 0.7. So again, we can see that ALTI has, that it has a lower BCI on average than VACAN. So back to the t distribution that we talked about last time. Oh, sorry. So yeah, just to say the result there is if we set our alpha as 0.05, which is kind of the standard alpha that people use a lot, but you can choose a different one. This is up to you. This is your choice. So we said, okay, we set alpha to 0.05 to say, and because the p-value is below that value, that 0.05, we reject the null hypothesis, being that the two sample means are the same. So the alternative hypothesis, of course, is that they are different, and we say they are statistically different because we did that test. We said there's a significant difference. So yeah, again, back to the t distribution. So this is a t distribution for the number of the degrees of freedom that we have. Remember that the t distribution, the curve will look slightly different. The less degrees of freedom you have, so the lesser your sample size, the smaller your sample size is, the tails will be a bit fatter, basically. And the higher your sample size, the tails will kind of like shrink, and it will be a bit more of a peak. And it will converge to a Z distribution, actually. We talked about that last time. And here we can plot what the t-value would be. The t-value would be for an alpha of 0.05. So to remind you what that means that there is 95% of the area under that curve that is left of that alpha, and only 0.0, so only 5%. Sorry, it's a two-tail test. So there's actually, there is actually two of these. There's one on each side. So 2.5% is there of that area. There should be, I should have put that here actually. There should be another line. It's symmetrical, so it should be around here. So 2.5% will be on that side as well. And 95% is kind of around the 0 there. It tells you that it is very likely, so if the two means are similar, then it's very likely that we'll get a t-statistic within that range, that confident range. Anything beyond, it means it's an extreme value. It's not impossible to get this by chance. It's just we say, but it is very unlikely. And our t value in this case is that it's very far. It's at 4.7. So we get this extreme t value, this t statistic. And of course, there's still a chance to get this by chance. But we say that it is unlikely to be simply caused by chance. So even if the two sample means are the same, you can still get an extreme t value by chance, but we say, it is so extreme that we don't think it's by chance. We think that this is because there's an actual difference in the two means. That's what the test is essentially doing. So I plotted, I put you where the t value was in comparison here, so you can see where it stands. Yeah, okay, so I hope that's clear. If you have any questions, you can write in the chat and we'll answer for you. So let's continue. What does this mean now that we have this significant difference? So the t-test really tells you, okay, it tells the difference in sample means. It's looking at the samples. Is the mean of sample 1 different from the mean of sample 2? And we concluded that there was a significant difference at the alpha level of 0.05. So we're quite confident that they are different sample means. So I put the histogram, the two histograms, I showed them to you earlier when we kind of inspected for normality, but I put them both on the same plot so you can see where they are. And we can see, okay, so Wakan kind of peaks there and the mean is going to be around there maybe. Altai is a bit more spread out, so it's not as dramatic of a peak. So it kind of goes like this, and yeah, it seems like the means could be slightly different, right? So this is our conclusion from the t-test, that the two samples have a different mean. And remember, we talked about confidence intervals in the first session and what that means. So remember, if you calculate a mean, you can also calculate the confidence interval. You can have a standard error. So the confidence intervals are calculated with the standard error. In the previous session, we had a formula to calculate this standard error, and it depends on your sample size. The higher sample size, the smaller your standard error will be, because you have more samples, so you're a lot more confident that the mean you have is close to the population mean. So remember, we're estimating parameter. The mean is a parameter. We're trying to infer something about a larger population. So we have a sample, but that sample will be representative. We hope it will be representative of a larger population. So we have this sample mean, and we know that our sample mean will be quite close to the population mean, but not exactly, right? That's why we need these confidence intervals. Using the standard error, we can calculate these confidence intervals, and a lot of the time people will use 95% confidence interval, but again, that's your choice. You can have 90% confidence interval, 70%. And what this confidence intervals tells you, is that the true population mean will be within that range. So for example, I'm just gonna go back a bit. Actually I have. So for example, the mean BCI for Vacan was 0.773. So this is the sample mean, but the population mean, kind of like the larger population, should be around that as well, but it won't be that exactly. So with the confidence intervals, we can say, okay, it will be between maybe, I don't know, 0.71 and 0.75. I didn't put the numbers here, so I don't know exactly what it is, but if you calculated this 95% interval, you'll end up with this lower and larger margin, and this will allow you to say with confidence, with 95% confidence, that the true population mean is within that range. It's close to our sample mean, and it could be a bit more, a bit less, but it won't be extremely more, extremely less. It will be it should be within that confidence interval. And this is what happens when you plot the confidence interval. So I just put both the means here. So the mean for Altai is there, the mean for Wakan is there, and the bars that you see are the confidence interval that I calculated, 95% confidence interval. And not surprisingly, they don't overlap because we with the t-test told us we had a significant difference. So naturally, we should not expect the population means either to be the same. And this is what happens here. This is kind of how the p-value is related to this confidence interval. If we had a p-value at the end of 0.05 exactly, you would see these two confidence intervals kind of like moving closer together and be like, there would be no overlap, but they would be exactly at the boundary. They would, so the lower, essentially the lower margin for the mean of vacant will be kind of like exactly above the higher margin for outside. So they would not overlap, but kind of like exactly there. And if we didn't find a significant difference in the sample means, so the t value would be a lot smaller and the p value would be a lot higher, so it would be more than 0.05, then we would also see these confidence intervals that they would overlap, which means similarly, like the same way we can't say that the sample means would be different between the two groups, the population means also like would be like, there will be some overlap. They might be the same actually. That's what it tells you. So yeah, I hope that was not too confusing. And yes, so this is it. So the t-test tells you there is a significant difference between your sample means, and the confidence intervals tell you that there is no overlap between the 95% confidence interval for the two assets of the population means. That's the main difference here. Okay, but they are related. Okay, now would be a good time to talk about, again, something you might have heard before. It's called type 1 and type 2 errors. All right. What are they? So, of course, we're going to do this statistical test, and we'll conclude, we'll take a decision, to either reject or accept, or failing to reject the null hypothesis. But what if we're wrong? Even if we did this test, what if the test itself is like not really robust? And we kind of have a wrong conclusion. Well, type 1 error is when you reject a null hypothesis which is actually true. So in our case, if the null hypothesis was true, then it means the two sample means were actually would be statistically the same. There would be no actual difference between the two means, and YK and outside have the same BCI, but we chose to reject it. So it's possible that we did a type 1 error. We rejected it, but maybe we should not have, and maybe the test was misleading. A type 2 error is essentially the other way around, when you don't reject a null hypothesis, so your conclusion will be that, oh, the sample means are actually the same, and we actually I'm being confused now. And we actually decided that the null hypothesis was actually true and that they were actually the same. So that's a type 2 error. So very often people put this in a table to like show a continuity table to show you what this means. So here's, okay, this is what we think the null hypothesis is. So that's H0, the null hypothesis. If we think it's true, but then you have, okay, what the null hypothesis really is, which is not, which is something we can't know for sure, but we hope that our test is robust and that we are correct. So if the null hypothesis is actually true, so that there is no difference, and we concluded that it was true, then okay, we are correct. So we are good, we're in the green. Of course, same thing, okay, if we reject the null hypothesis, so we think the null hypothesis is false, and we are correct, and the null hypothesis indeed really is false, and there is a significant difference, then we're still in the green. And these are so that means that there really is no effect. But again, if we think the null hypothesis is true, but we did not reject it, but actually we should have, then it is a type 2 error. There actually is an effect, even though we thought there was not. And here is the type 1 error, is when we reject the null hypothesis, but in fact there is no difference statistically. We simply failed to test for this. We thought there was an effect, but actually there is not. And of course here is like, okay, we are correct. There is there really is an effect, so we should reject the null hypothesis. The null hypothesis is not true. So how can we avoid these errors? Of course, there are ways to kind of like set the scene for us and make sure that our tests are indeed correct and that we are drawing the right conclusions. Well, first of all, we could have a large sample size. If we have a low sample size, it will be harder to detect differences. So, of course, the test should be, so a t-test, for example, is tailored for low sample size. So even if you have a low sample size with a t-test, you should still be able to draw the right conclusions. But increasing your sample size does something that we call, it increases the statistical power. It increases the power of your test. And it will essentially reduce the type 1 errors. So, the type 2 errors. So, in this case, if we have a low sample size, maybe it is more likely that we will conclude that there is no difference when actually there is one. So this is the type 2 error. There actually is an effect. And if we had a larger sample size, maybe we would have been able to detect that effect. Another thing is that if your study design is a bit flawed, for example, like we are measuring BCI, what if the method, and if you remember from last week, there's a bunch of methods to calculate BCI. What if we chose the wrong method? Maybe the way we calculate BCI is not great. The sampling design, of course, what if we really sampled very specific leopards? Like what if the way you caught leopards in Altai was very biased? So again, you have to really think about your study design. Before reaching a conclusion, you need to be sure that the way you sample, the way you obtain your data is makes sense, especially makes sense with the test that you're using. So in the case of the t-test, one of the assumptions, remember, is that the data points are independent from one another. What if they are? What if during your sampling, you actually did kind of like create some dependency there, and then your t-test will be flawed and you will reach the wrong conclusions. You can adjust the alpha. So remember, by default, people use the 0.05. This is really not something you have to use. This is kind of like a default that people do use because, you know, what should we use, right? 95% certainty, confidence seems like a nice number, I guess. So that's what we use, but you could use a different threshold. So if you increase, like just picture this, if you increase your level, so if you make it more strict, of course, it will be harder to detect differences, because even if it's lower than 0.05, your p-value, you might still end up concluding that there is no difference because you set your alpha level very low. You put it at 0.01, for example. And of course, this will affect your conclusion. Your conclusion depends on that alpha that you're setting. This is the threshold you're allowing yourself. You're saying, okay, this is the threshold at which I say, okay, this is where there is a significant difference or not. Of course, you can do the other way around. You can be more conservative in your alpha and set it really low, quite high, 0.1. So people don't usually do that. It's 0.1 it is quite high, but it will reduce the chance of doing a type 1 error. Wait, I'm getting confused with these type 1 and type 2 errors myself.
Yeah, no, it'll reduce the chance of a type 1 error.
Exactly right. So you're more conservative. So it is.
No, you're less conservative. Generally, in this terminology, if you're being more conservative, you're trying to reduce the chance of a type 2 error, because you'd rather not find a pattern, even though there is one, than falsely conclude that there is a pattern.
Yeah. By the way, that's also something you should ask yourself, is whether you are more willing, because there's a trade-off, of course, sometimes, especially if you're choosing a different alpha. Are you willing to make a type 1 error over a type 2 error or not? Maybe you'd rather do, maybe you'd rather be sure that there's an effect. Let's think about, for example, in medicine, maybe like if you do a different practice, like a different type of surgery, you want to be sure that this is worth it, maybe because the risks are higher.
And also, like in physics, generally they do set a much more conservative alpha because they tend to have much more precise measurements and less noise in their systems than we do. So they would,
That's true.
like 0.01 is a very standard alpha in physics. Lots of fields.
That's true. In ecology, we do usually have a lot of noise. So yeah, that's true. But yeah, and same with conservation. Again, with conservation practice, the stakes may be really high. So if you want to, let's say you're doing a reintroduction program and you want to like say, okay, did the body condition improve or became lesser after the reintroduction? If you're dealing with an endangered species, like the consequences is huge, you know, like there's a high risk. So you want to be really sure that the reintroduction maybe is worth it. And maybe you want to, that's why maybe you want to be really sure to be detecting an effect rather than detecting an effect when actually there is no effect. Okay, and again, of course, you have to make sure that no key assumptions have been violated in your test, because if you do, of course, you might have a false the p-value may be, you know, not what it should be because you violated these assumptions. So the test is not valid. Maybe doing a t-test is not suitable for the kind of data you have, and maybe you have to use a different approach. So these are, you know, this is not a comprehensive list, but these are things you can do to reduce errors. But if you're very sure what you're doing, then you go ahead, do your test, reach your conclusion. Another thing I should mention probably here is that if your p-value is very close to your threshold, to your to the critical value you assign to your alpha, maybe, you know, don't rush into you know, concluding that there's a significant difference. If your alpha is 0.05 and your p-value is 0.047, so super close to it, maybe it is worth discussing. Maybe it is worth considering that maybe it could have been on the other side. So that's in research, that's usually what people do. Like if the p-value is really close to your alpha, maybe it is worth talking about it. Yeah, okay, so, and okay, maybe one last thing to mention about this is that you should not do your test and then later decide your alpha because you want to find a particular result. All of this is something you have to set before the test. This is for good practice. So the sampling, the data you select for the test, the alpha level you're setting should be done before you see the result. Because of course, if you see, okay, the p-value is at 0.04, and maybe you know, you really want to find a difference because, okay, maybe it's more publishable. Of course, setting an alpha at 0.05 then makes you, okay, well, there's a significant difference. But what if it made more sense for you to actually have an alpha at 0.01? So you're a bit more strict. That's something you should decide before doing the test.
Okay, I'll start.
I guess. Oh yeah, sorry. I just put that little animation. This is to tell you, okay, just to again reinforce. So this is the conclusion we have, you know, with our t-test between the BCI of the two locations. So remember, the t-test was we thought the null hypothesis was not true. We rejected it because we had a p-value very small, way below our alpha level. So we are in that region. It doesn't mean we're right. It just means, okay, well, the actual, the truth there could be that the hypothesis really is, not really is false, and we should indeed reject it. So we could be in that region here, and we could be correct, but we could also be making a type 1 error where we are rejecting the null hypothesis when actually there is no effect. So just something to bear in mind every time you do a test, just ask yourself, what are the chances that you're making a type 1 error? Or in the case that you are not rejecting the null hypothesis, what is the chance that you're making a type 2 error? All right, let's continue. So over to you, Anne.
So now from t-tests, we will move to ANOVAs. Now t-tests typically help you figure out if there is any difference between two sample means, or basically two population means. But what if whatever you're testing has more than 3 levels of factors? So instead of just comparing leopards between Altai and Wakan, let's say we had samples for one more area. In such a scenario, what we would do is use a one-way ANOVA. Now, ANOVA is a test of variance. But one thing, important thing to remember here is, although we are testing variance in order to see if there's a difference, the conclusions we're making is about the sample means. Okay, so that can be like a little confusing. So if you remember, in the first class, we had covered variance, and how we calculate variance is by squaring the differences from the mean for each sample and then dividing it by our degrees of freedom. Now, this differences, deviations from the mean in the context of ANOVA are referred to as sum of squares, because basically what you're doing is just adding up all the square values of the deviations from the mean. Now, sum of SST, these are some common terms we'll be using in the calculation of ANOVA. SST refers to sum of squares total, so that would be all of the sum of squares. Then we have SSW, which is sum of squares within. So within means within group. So let's say, for example, in our hypothetical leopard situation where we have samples from 3 different areas, this would be the difference of each sample from the mean of each area. So each sample in Altai divide minus the mean of Altai, whole thing squared plus and added. Oh no. And similarly for each of the 3 regions. Then we have sum of squares between groups. Between groups would be the sum of square, the mean of the group, that's of the group minus from the global mean. So global mean is the mean of all of the samples. So let's say we had 5 samples from Altai, 5 samples from Bakan, and 5 samples from hypothetical third population. The mean of all 3 of these is what we refer to here as X double bar, and X bar is the mean for each one of these. And it's the summation of this. So you have to remember, each one of these calculations is being done at the level of one sample. So basically what the summation means is, if there were 5 samples in that group, this whole thing will be into 5. And so that's the terminology. And it's a feature of the sum of squares that the total sum of squares is always the sum of the within sample sum of squares plus the between sample sum of squares. And for ANOVA, what we do is calculate the F statistic. So you know how we calculated the T statistic and the Z statistic and used its value compared to the number of samples you had to figure out whether the test was significantly different or not. In ANOVA, what we use is something called the F statistic. Now the calculation of F statistic for one-way ANOVA is pretty simple. It's the mean square bit. So it's the mean square between groups divided by the mean square within groups, which is calculated as given here. That would be the sum of squares between groups divided by the number of categories. C is the number of categories minus 1. So if you have 3 factors, it will be 3 minus 1, so 2. And sum of squares between groups, within groups divided by the total number of samples you have. So if we had 5 leopards at each of the 3 sites, that would be 15 minus the number of categories that you have. And basically what C minus 1 and N minus C here represent is the degrees of freedom for these particular calculations for the sum of squares. And okay.